Hey everyone, and welcome. Today, we're going to pull back the curtain on something you probably use every single day, a mirror. But we're not just going to see ourselves. Oh no, we are going to see the incredible, mind-bending physics hiding behind the glass. We're going to figure out how a simple, shiny surface can bend reality to show us a perfect, yet completely flipped version of ourselves.
And it all starts with a question I know you've asked yourself before, probably while standing in your kitchen. You pick up a shiny spoon, you look into the curvy part, and bam, there you are. But you're upside down. What is going on there?
I know, it feels like some kind of weird magic trick, but I promise you it's not. It's pure, elegant science. The answer is hiding in the beautiful and surprisingly simple rules of physics. And trust me, by the time we're done here, you'll know exactly why that spoon turns your world upside down. Okay, so to crack the case of the mirror, we first have to get to know the main character in this whole story, light. More specifically, we need to know what happens when light actually hits something. And that brings us to our core concept, reflection. You know, it's just a fancy word for light bouncing. Seriously, just imagine light as zillions of tiny, super fast bouncy balls. When they hit something smooth and shiny, like a mirror, they all bounce off in a really neat, predictable, and organized way.
Now, not all bouncing is created equal. On a super smooth surface like a mirror, all those light rays bounce off at the exact same angle. We call that specular reflection. But on a rough surface, like, say, this desk or a piece of paper, the light rays hit all these little bumps and scatter in every direction. That's diffuse reflection. But here's the kicker. The same simple rule is behind both of them.
And here it is, the one law to rule them all, and it is so beautifully simple. The angle the light comes in at, we call that the angle of incidence, is exactly the same as the angle it bounces off at, the angle of reflection, every single time. This one little rule is the master key to unlocking every secret a mirror holds. So let's take that law and apply it to the mirror you probably looked at this morning. The good old-fashioned, simple, flat, plain mirror.
Okay, now here's where things get a little weird. Because the real magic trick, it's happening inside your own head. See, when light from your face hits that mirror and bounces into your eyes, your brain doesn't actually know it bounced. It's wired to think light always travels in a straight line. So your brain traces those reflected rays backward in a straight line to a point that looks like it's behind the mirror. And that's where it creates the virtual you that you see staring back. So this brain trick creates an image with some very specific qualities. For one, it's upright. You're not upside down, but it's also laterally inverted. Your left hand is its right hand. The image also looks like it's the same distance behind the mirror as you are in front of it, and it's the exact same size. And because that image isn't physically there, you can't put a piece of paper behind the mirror and see it, we call it a virtual image. And here is the perfect real-world example of that left-right flip. You've definitely seen this, right? The word ambulance is written backward on the front of the vehicle for one simple reason, so that when you see it coming up behind you in your rearview mirror, the mirror flips it back the right way so you can read it instantly. It's a super clever use of physics that literally saves lives. Okay, flat mirrors? Check. We've got those down. But what happens when we start to curve the mirror? Well, this is where things get really fun. And it brings us right back to our original mystery, the spoon. So there are really two main ways to curve a mirror. Concave mirrors curve inward, like you're looking into a cave. That's the inside of the spoon. Convex mirrors bulge outward, or they flex out. That's the back of the spoon. Just remember, cave in and flex out, and you'll never mix them up.
Now, to talk about these properly, we just need a few key terms. The pole is easy. That's just the dead center of the mirror. The center of curvature is a bit weird, but just imagine your mirror is a small slice of a giant glass ball. The center of curvature would be the very center of that big ball. But the most important one, the real star of the show, is the principal focus. Think of this as the mirror's sweet spot. It's the one special point where all the light gets concentrated.
So how can we possibly predict what an image will look like in one of these crazy curved mirrors? Well, we could do a ton of complicated math. Or we can use a really simple drawing method that's more like following a recipe. It's called ray tracing. Now, the great thing is, we don't need to track every single ray of light. We only need to follow the path of three special principal rays, because their behavior is always super predictable. A ray that comes in straight and parallel reflects through the focus.
A ray that goes through the focus first reflects out straight and parallel, and a ray that goes through the center of curvature just bounces straight back on itself. And here's the magic. Wherever those three reflected rays cross, that's exactly where your image is going to show up.
So, after all that, what's the bottom line? Well, for a convex mirror, the back of the spoon, the result is always the same. No surprises. The image will always be upright, smaller, and virtual. But for a concave mirror, the inside of the spoon, now that's a different story. It's a total wild card. The image can be real, virtual, upside down, right side up, bigger or smaller. It all depends on how close you are to it.
And this isn't just some abstract theory or lines on a page. These properties are purposefully engineered into really useful tools that are all around us. Let's take a look at where this physics actually shows up in real life. Think about your car's passenger side mirror. That's a convex mirror. It bulges out on purpose to give you a much wider field of view so you can see more of the road and avoid blind spots. But what's the trade-off? Well, just like we saw in the chart, the image is always diminished or smaller. And that's exactly why they have that warning printed on them. Objects in mirror are closer than they appear.
Now on the flip side, a makeup or a shaving mirror, that's a concave mirror. And it's designed so that you put your face very close to it, inside its focal length. And what happens when you do that? The reflected rays create a magnified, upright, virtual image. It's the perfect proof of how just changing your position in front of a concave mirror completely changes the reflection.
And here's another really cool use for concave mirrors. In a flashlight or a car headlight, the bright little bulb is placed exactly at the focal point. The curved mirror then collects all that scattered light and reflects it forward as a powerful, focused, parallel beam. It's basically our F-ray rule, just running in reverse. Now, drawing ray diagrams is awesome for getting a feel for what's happening, but engineers and physicists, they need perfect precision. That's where this little gem comes in, the mirror equation. Think of it as the secret code. F is the focal length, DO is how far the object is, and DI is how far the image is. You just plug in the numbers, and you can calculate exactly where an image will form, down to the millimeter. So there you have it. From an upside-down spoon to the safety features in your car and the flashlight in your drawer, it all comes down to that one single, simple law of reflection. It just goes to show you that underneath the surface of all these everyday things, there are these elegant and powerful rules running the show. So the question I want to leave you with is this: what other invisible physics is hiding in plain sight, just waiting for you to notice?